So in the last part of the lecture, we asked ourselves an important question that what if we had some prior information or some prior distribution over the parameters W with some hyperparameter lambda and gamma. Now, is there a way to incorporate this information into our optimization formulation, right? So is there an optimization formulation? That takes in this prior information and the likelihood function, which is I equal to 1 to m p of yi given xi and parameter w. So now we are considering that w is a random variable and we have the prior information on w. So can we combine these two information and get a new estimate of the parameter? Sorry, just w new. Sorry for the typo. Can we get a new formulation w new that may be perhaps better than the WMLE, where the better is some measure that we'll see later. What is better mean over here, right? So can we combine the two information together? Can we combine the prior and the likelihood, and can we design an optimization formulation that gives us a new W that solves the problem of our prediction of new y given some new data point x? And the answer seems to be yes. And now in this part of the lecture, we are going to show you how to do it. What is this optimization formulation, and how to actually compute this new estimate of the parameter W. But before we begin to do it, we just wanted to cover some basic probabilistic part. What does this error actually mean graphically or practically, so that you are much more mathematically prepared to deal with the probabilistic formulations that we are going to use in the later parts of this lecture. So let's dive deeper into understanding the probabilistic formulations. So we discussed that yi is given by the mapping function fw phi of xi. So here we are not considering that this is WMLE or this W new. We just assume that there is some true parameter W. We denote as a W star, some true parameter W star, which produces this mapping, plus some small noise epsilon I. Right? And each of these noises are IID. Right? So in this entire equation, we can just rewrite it to highlight this fact. In this equation, yi is equals to, which is simply W star times transpose times phi of xi plus epsilon I, which is our random variable. So in this entire equation, there's only one, on the right hand side, there's only one random variable, epsilon I. So if we take expectation on both the sides, so expectation of yi given xi is basically expectation of W star transpose times phi of xi plus epsilon I. So since this is not a random variable, xi is given, and we all W is not a random variable. So if from the basics of statistics, this is simply W star transpose times phi of xi plus the expected value of epsilon I. So as you can see, what is the expected value of y? So the expected value of epsilon I, if we assume that this epsilon I has a distribution which has zero mean. So let's consider a simple example where this is a normal distribution with mean zero and some variance sigma square. So now the expectation of yi given xi is simply w star transpose times phi of xi, because the expected value of the noise epsilon I is 0, which is the mean. So in case of normal distribution, when you compute the expectation, you'll find that it turns out to be the mean of the distribution. So this is expected value of epsilon I is 0. So the expected value of y given xi is just the functional mapping fw of phi of xi. So what does it actually mean? And now there is also one more interesting fact actually. What is the distribution? What is the distribution P of yi given xi and the penetration parameter? What is this distribution, right? So this distribution, we assume that the epsilon I has a normal distribution, right? So the distribution of yi is simply given by the normal distribution. It will also have the normal distribution because the yi are given, the expected value of y is given by this, and the noise, which is a random variable, is governed by this normal distribution. So the distribution of yi will also be governed by this normal distribution, but with the mean having a function mapping fw of phi of xi. So this is the normal distribution of yi given the functional mapping phi of xi and variance sigma square. Now we can give you a more practical interpretation as to what does it mean. So assume here is your assume that x is a scalar. This is x and this is fw of phi of x. So now let's assume that you observe a value some xi. So just draw it over here. This represents x equal to xi. And likewise, we can plug in the value of w and we can get some value fw of phi of xi. But as we know that we also have, so the yi, so this is equal to the yi, right? This is supposed to be y, but with some small noise epsilon I, right? So we can indicate it like this. Now epsilon I has distribution. It means that if yi differs from this value, let's suppose by a small amount delta, then we can compute that the probability of that small difference, which is the error, by computing the probability of this error delta by plugging it in the normal distribution with mean 0 and variance sigma square, right? So we'll have a small error over, so we can draw a distribution over here with a different color. I'll try to draw it as accurately as possible. We can extend it further. So as we can see, the expected value of yi given the input xi and the parameters w is simply fw of phi of xi. But the output will have some noise. The output is there's some noise, and this is what the distribution looks like, right? So the variance of this distribution is same as a variance of the noise, since yi is equals to fw of phi of xi plus some small noise epsilon I. So the variance in the output would be the same as the variance in the noise, and this is exactly what we have represented. So now you can see effectively the yi's have a normal distribution with mean being fw of phi of xi, but there's some distribution around that value, and that distribution is again going to the normal distribution because epsilon I have normal distribution, and the variance of this distribution will be the same as the variance of this noise term. So this distribution has some variance sigma square. So we can simply write if yi is fw of phi of xi plus epsilon I, and none of this is random variable over here, then the expected value of yi given xi, and we can write a parameterization as w over here to denote that this parameter is by w, is simply fw of phi of xi. We can also write, instead of conditioning it on xi, sometimes if you're referring some book, they can also write it as phi of xi, which is same thing, because what we are assuming that this phi is not a random mapping, this is a deterministic mapping. So depending, given a value of xi, there's a 1-to-1 mapping with xi and phi of xi. So that's why writing here xi phi of xi, it means the same thing, almost the same thing, because we are always assuming that instead of learning this mapping on xi, we are learning this mapping on phi of xi. So this is what it, so the expected value is given by this, and the distribution p of yi given xi is now going to follow a normal distribution, the distribution of this error epsilon I, right? Because there's always a noise. The output, the y is given by this with some noise. So the expected, the mean would be, so it should follow normal distribution y with mean fw, the functional mapping over xi, and the variance sigma square, which is the same as the variance of this epsilon I. So we just write a finite equation as, if yi is given by some mapping, function mapping f phi of xi plus epsilon I, where this has some distribution p with some mean 0 and some variance sigma square. This is normal distribution, mean 0 and variance sigma square. Then the distribution of yi given xi and parameterization w is simply the same distribution p of yi with mean being fw of phi of xi. This is a normal distribution. We just denoted n by p. And variance sigma square. And the expected value of yi given xi is simply fw of phi of xi. So in the next few lectures, perhaps instead of writing this, we can use this formulation. We can write it as n of, we can replace this n p by n, and we can have this representation as well, yi given fw of phi of xi. So just to let you prepare for this kind of notation, we just explained it, how everything is related. So now you are more sort of adapted to dealing with the probabilistic representation, the probabilistic equations that we are going to use in this lecture.